So let's start today's lecture. Oh, okay. So we'll be staying on the same line. Namely, our topic is communication. Last week, we have two parties, Alice and Bob. And we have a protocol. Just the 3-round protocol, very simple 3-round protocol, sending integer from Alice to Bob, and 1 bit from Bob to Alice, and the integer from Alice to Bob, and small computation in the Bob side. This is a protocol. Then, following this protocol, Alice can prove something, actually x. Alice can prove that integer x is a quadratic residue to Bob. Alice can prove that this x is a quadratic residue against Bob, but Alice does not send any information, does not reveal any information about the answer. X is y square mod m. So Alice does not reveal any information about this answer y to Bob, but still Alice can convince Bob that this x is a quadratic residue. So really amazing. So that's what we call zero knowledge proofs. Okay. So if the answer is yes, Alice can convince Bob without revealing any answer. And if the answer is no, so x is not a quadratic residue, then if they follow this communication protocol, then Alice cannot convince Bob. In other words, Bob does not accept the input with probability 1/2. So just we can repeat this process, then that probability can be bigger and bigger. Okay, so this is what we did last week, and today the idea, the topic is the same, but okay. So the topic is still communication, but today's problem is more directly related to communication. So our chapter 5 is communication complexity. Okay, our model is the same. We have two parties, Alice and Bob, and some communication protocol. Okay. But the difference is Alice has her own input x, and Bob has his own input y. Okay. Now Alice has its own input, and Bob has his own input also. And the task is compute. They need to compute f of x and y for some specific function f. Okay, so this is the job. This is the task, and the goal is to minimize. The number of bits for communication. So this is our today's problem. Okay? Once again, we have two parties, Alice and Bob. Alice has its own input x, Bob has its own input y, and their task is to compute some specific function value, f of x and y. Okay? With a minimum number of bits for communication. Of course, Alice does not know input y. Bob does not know input x. So they need some kind of, some kind of communication to compute this value. So we have to minimize the number of bits to exchange between Bob and Alice. Okay. Let's quickly go to an example because it's easy to understand the problem. So example 1. X and y are subsets of 1 through n. And f of xy okay? So, Alice, Bob, Alice has an input x is equal to something like 1, 2, 8, 9. And Bob has input y 3, 6, 7. Okay, so this is the situation. And the important assumption is that Alice and Bob know this ground set. So Alice and Bob do know this ground set 1 through n, but they don't know, Alice does not know Bob's y, and Bob does not know Alice's x. So they need to compute this function. What is this function? This is quite easy, simple. Maximum value of x union y. So in this case, what is the answer? The answer is 9, of course. Right? Okay. So what is the protocol? What is the protocol? Okay. I'll tell you the important fact about this problem. There is always trivial algorithm. Okay. Always exists a trivial protocol. Meaning, Alice sends x. Okay. This is trivial, always trivial algorithm protocol. Alice sends her input x to Bob. Okay, then of course Bob can compute function value x, f of x and y. Right? It's of course possible. Of course possible. So in this case, what is the communication complexity? What is the communication complexity? Communication complexity let's use just CC. Communication complexity is, we have at most n numbers in x, and remember that we are counting the number of bits. So each number may have log n bits. So that means communication complexity is something like n log n. Right? because at most n numbers, and each number has something like a log n bits. But it turns out this is too much. It's too much. Actually, this is not n log n, but n. Why? Because just remember our assumption. Alice and Bob do know this ground set. This ground set 1 through n. That means, just Alice sends Bob. Not these numbers directly, but in this case, 1, 0, 1, 0, 0, 0, 0. I don't know. Yeah. This bit sequence. Alice just send Bob this bit sequence, then Bob can know that Alice has 1, 2, 8, and 9. Because, of course, oh, I'm sorry. I made a mistake. Okay. Yeah. This one. So this first bit is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So what Alice has to send is not direct numbers, but this bit sequence. This bit sequence is enough. That means the communication complexity of this trivial protocol is, this linear. Okay. Of course, beta algorithm? Of course, we have a beta algorithm. But that is just sending Alice just sends her biggest number. Okay? In that case, Alice sends her biggest number 9. Then Bob can see, Bob can figure out that that's the biggest number in the set x union y is 9, because Bob does not have a bigger number than 9. Okay? So in this case, communication complexity is log n, because Alice just sends the biggest number. We need log n bits for one number. Okay, so far so good. So everything's clear? Okay? Good. Now, second example. The same. Same x and y. So they are both a subset of 1 through n. And function x is okay. Function x is the average value of x union y. Okay? So, I don't know. What is the average value? So in this case, average value of 1, 2, 8, 9, 3, 6, 7, I don't know. Anyway, that is a function f. Okay, do you understand the problem? Good. Now, what is your protocol? What is the protocol? What is the algorithm? Oh. So what of this? Alice just sends the average of her x. Is this okay? Is this enough? No, yeah, no, that's correct. This is no. Because in this case, the Alice's average is, I don't know, 1 to 8, 9. Her average is 5, I guess. Yeah. But if Alice sends just 5, then Bob doesn't know, how many numbers does she have. Yeah, it's completely different. It's completely different. Alice may have only 1, 5, or Alice may have 1 and 9, and Alice may have these 4 numbers. There are many, many different cases. And Bob does need to know the number of numbers. Okay. I'm sorry, I have a cold. So, Alice sends both the average of her x, and the number of her number. So, the correct algorithm sends the number size number. The number of the number. Size x and the average of x, or the sum. X. So this is it. What means communication complexity is equal to log n. Log n, right? Because Alice need to send 2 numbers, but both need log n bits. So it's not a big problem, just a big O of log n bit. Okay, well, it's easy. It's easy. Now we are getting to the bit harder problem. Okay, now example 3. X and Y are the same as before, and now function f of xy is not average, but the median of the union of x and y. What is median? Median is just the middle number. Okay? So in this case, 1, 2, 3, 6, 7. Okay, in this case, so union of x and y is 1, 3, 1, 2, 3, 6, 7, 8, 9. And the median is exactly the middle number. In this case, that is 6. Okay? Formally speaking, 2x as the size of x plus y divided by 2 largest. So this is our definition of the median in this lecture. Okay, so we have 7. We have 7, and divided by 2 is 3.5. Is a Gaussian, it's a round up. Then the fourth largest, 1, 2, 3, 4. Fourth largest is our definition of the median. This is not that easy. Not that easy. Can you come up with some protocol other than trivial one? Or we have always trivial ones, meaning just sending everything. That is of course possible, but we can do better. We can do better. Okay, I'll show you our protocol. This is our algorithm. Actually, this is not a very good algorithm. This is not very good algorithm. I'll show you another algorithm that is much better than this. But anyway, this is still non-trivial. This is still This is already non-trivial. Step 0. Step 0 is a kind of a preparation. Alice and Bob send the size of the input to each other. So in that case, Alice sends 4 to Bob, and Bob sends 3 to Alice. Just the size of the inputs. Okay, this is a preparation. Now the main part of the algorithm, number 1, step 1. Okay. Now, in that example, n is 10. N is 10. And Alice sends the number of items which are at least n over 2. So at least 5. At least 5. In that case, that is 2. Okay? So Alice sends 2 to Bob. Then Okay. Now Bob can tell whether the median is at least 1/2 or less, at least n/2 or less. Why? For example, Alice has Bob has y, and okay. So suppose, just think of this situation. Just think of easy example. Alice has 8 numbers. Alice has 8 numbers, and Bob has 12 numbers. And Alice's number, in Alice's case side, she has 3 numbers less than n/2. This side, first side, and 8 numbers in the second side. Okay? Bob has 10 numbers in this side, and only 2 numbers that side. And in this case, Bob sends what? Bob sends 3. No, Alice sends, yes, I'm sorry, 5. Alice sends 5 to Bob. Okay? But remember that Bob does know that Alice has 8 numbers. That means Alice has 3 numbers in this side, and Bob has 10 numbers this side. The total number in the first side is 13. Okay? That means, Bob can figure out that the median is this side, first side, right? Because we have 20 numbers in total, and the first side has 13 numbers. So obviously, the median should be there. That means Bob can figure out our median should be in this side. Right? Yeah. Okay. Okay. Now we know both of them, both Alice and Bob know that the median should be in the first half, of the numbers. Then we just repeat this. Okay? Then they said the number, the border is here. Border is n/4. n/4, and exactly does the same thing. Okay? Then this is exactly a binary search. The median should be this side, then the median should be this side or that side, and do the same thing. Just repeatedly. This is doing the binary search. Then, after log n rounds of this step, of this repetition, then the area of the candidate, area of the median, should be very small. Just just one number, just the constant numbers. Okay. So we are done. So what is the communication complexity? log n bit. First log n bit, and this is also log n bit. Log n bit. Oh, this is just single bit. Notified to Alice is just a single bit. So just one bit. And how many rounds do you need to repeat? Of course, log n rounds, because this is a binary search, right? That means communication complexity is log n squared. Because in each single round, we need log n bits for communication, and we need log n rounds. That means log n times log n is log n squared. Good. But as I said, we do have better algorithm. We can remove this too. Okay, I'll show you. Or maybe you can come up with this algorithm. This algorithm is clever, but maybe not crazily clever. Yeah, probably you can come up with the idea. But the next one, well, this is really clever. I hope you can feel that the next one is really nice. We have a much better algorithm. Step 0. Again, this is a preparation. Okay. The first step 0, is just for preparation. They do exactly the same thing as before, just sending the size of their input to each other. Here, we make a important assumption that the size of x and y are the same. Okay. Without loss of generality, we can assume that the size of the x is the same as the size of y. Otherwise, if the size is different, then we can add the same number of 0 and n plus 1 to the smaller set. Okay. For example, suppose that the size of x is 8, size of y is equal to 12. Then we add, x is equal to something like this. Then we add 2 zeros and 2n plus 1, 11. Okay? We add 2 2 zeros and 2 11s, where n is 10. Where n is 10, maybe 10 is a little bit too small. Maybe so we have 2 zeros and 2 n plus 1s. Then the size of the x becomes 12. It's the same as the size of y. And of course, the median does not change. Right? Okay. Well, there's a couple of details, small details. For example, if what about if the size of the x is an odd number? That's a small thing. So just you can consider what should be done by yourself. Okay, so it's a not big problem. So now we can assume that the size of the x is equal to the size of y. Now we are going to the main step. So now Alice checks which is the case. We have two cases, case 1 and case 2. Alice looks at her numbers and check which is the case about her numbers. Case 1, more items are at least 1/2. Number 2, case 2, more items are, Case 1, more items are more than at least n over 2. More items are less than n over 2. Okay? So I check which is the case. And of course, send it to Bob. Notify it to Bob. Now, Bob does the same thing. Bob makes the same check about his numbers. Okay. Now we have a nice. Now we can do a very important observation, important analysis. Okay. For example, This is one possibility. Okay, this is one possibility. We have a middle, n over 2 here, and Alice has more number here, but Bob has more numbers here. This is kind of a cross. This is one possibility. What is the other possibility? Of course, of course, we have a kind of a similar possibility, less more and more less, but that's the same thing, almost the same thing. So this is just cross, and this is kind of parallel. So this is the second case. This is the second possibility. But Alice has more numbers here, and Bob has also more numbers here. This is the same side. This is the same side, or parallel, not cross. Okay. Now, here's important. Here's a very important observation. In this case, case A, in this case. Okay. Now is a very important observation. Alice can discard the smallest m over 2 items. M is a number of x and number of y, because they do not include the median. And Bob also can discard the smaller. Similar for Bob. This is not very similar. I should write it down. I'm sorry. So it's similar, but not smallest, but n over 2 largest items. Okay. Let's see why this is okay. Suppose that this is the case. Suppose that this is the case. Okay? So Alice has 12 numbers, here and 4 numbers there. Bob has 6 and 10. Okay, both have 16 numbers. 16 numbers. What's the median? Median is the 16th largest. 16th largest, right? Because they have 32 numbers in total. So due to our definition, the median is the 16th largest. Okay. What I'm saying is Alice can discard 8 numbers from here. Smallest 8 numbers from here. Bob can discard largest 8 numbers from here. Why is this okay? Okay, we have 12 numbers and 8. We have 10 numbers, 8. Why there is no median in these 8 numbers? This is an elementary school calculation. Suppose that we do have a median in these 8 numbers, then what happens? The number of numbers, the number of items, which is at most median, is 8 plus 6, 14. Contradiction. Right? Once again, suppose that there's a median in these 8 numbers. Then the number of items at most median is at most 8 plus 6 is 14. That is a contradiction. Because the median is 16th largest. So that's why we can safely discard these 8 numbers. And exactly the same reason, for the same reason, Bob can discard these 8 numbers. Importantly, by discarding those 8 numbers in Alice's side and Bob's side, does not change the median. Okay? Does not change the median. That means if this case happens, then Bob and Alice can decrease the number of items from 32 to 16. Very good progress. Very good progress. Okay? Then what about this case? What about this case? This case is much, much easier because the median should be here, right? That means in this case, the range of the median becomes the whole thing to 1/2. The same thing as before. If this case happens, the number of candidates becomes 1/2. If this case happens, the range of the candidate becomes 1/2. Just repeat. Just repeat. So if this case happens, then we can exactly do the same thing. If this case happens, then the borderline becomes 1 n over 4. That's a change. That's a change. But what we do is just the same as before. Okay? So just repeat. Just repeat 1, 2. And by doing 1 round, the size, this case, the size becomes 1/2. Or the range becomes 1/2. Okay? And we need just 1 bit. 1 bit or 2 bits, I don't know. Maybe 2 bits. Maybe 2 bits for 1 round. Number 0 is a preparation. So we do need a log n bits for the step 0, but that is only once. That is only once. So we don't have to care. We don't have to worry about that. Just only once. So repeating 1 to 2 log n times, then the size or the range becomes constant. We are done. We are done. Okay? This is very clever. This is really, really clever. Yeah, I was surprised. And it's, in our field, there are many clever algorithms. Yeah, I already showed you several nice algorithms. It's really amazing. Yeah. Okay. Good. So all the examples I showed you have relatively small communication complexities, like log n squared. Something like small complexity, communication complexity. But that is not always correct. That is not always true. For some problem, we need much more communications. So I'll show you such a difficult example next. So, example 5. Okay, so this is our next example. Well, actually, should be example 4 because it's I skipped example 4, but the example 4 is coming. Is coming in a moment. Okay. So this is example 5. X and y is the same as before, and the function is has only 2 values, 0 and 1. If x and y does not have a common item, does not disjoint, x and y are disjoint, then the value is 0. If x and y have a common element, same element, then the function value is 1. oh, this is just like you are talking to your girlfriend or boyfriend by phone. You know, no, you wanna go to dinner to some restaurant. No, what you are thinking is something like it's several 4 or 5 restaurant. She also are thinking 3 4 restaurant. You wanna find if they're the same restaurant, your mind and in her mind. The question is there a better protocol? Is there a better protocol or better algorithm rather than sending all your candidates to her? Once again, you are thinking 5 different restaurants in your mind. She's also thinking something like 6 restaurants in her mind. The question is, where is the same restaurant in your mind and in her mind? Is there any better algorithm rather than sending all your restaurants to her? The answer is no. The answer is no. There is no better way than sending everything. Yeah, I'll prove that fact a bit later. But for preparation, I'll show you easier problem. Example 4. Oh, sorry. 0. So Alice and Bob have n-bit strings. N-bit strings. For example, Alice has this 3-bit string, 101, and Bob has this 3-bit string, 001. The function f is just parity. Function f is just a parity of both strings. The function value becomes 0 if the total number of ones in x and y is even. The function value becomes 1 if the total number of ones is odd. Or in that case, the number of ones is 3. That is odd. Okay? So the function value is 1. Of course, this is a very easy problem. A very easy problem. So just Alice sends Bob the number of ones in her string. Okay? That's enough. That is what? That is log n. Communication complexity is log n. Okay? But this log n is necessary. This log n is necessary. So I can prove that there is no better algorithm than log n. This is a protocol. Alice sends her parity 0 or 1, and Bob sends his parity 0 or 1. Then both sides can tell the function value. And we can look at this protocol as follows. Okay. Just look at this protocol as follows. Alice sends her parity 1 or 0 to Bob, and then Bob sends his parity 1 or 0 to Alice. Then looking at this tree, we have 4 different cases. Right? 4 different cases means this is Alice odd and Bob odd. In total, it's even. Alice odd, Bob even, then odd. Alice even, Bob odd, is odd. So this is 4 different cases. Okay. Now, it's very important to know that for this problem, you need to distinguish these 4 cases. Right? You need to distinguish these 4 cases. And, in order to distinguish 4 different cases, you need 2 bits. You need 2 bits. Because this is a binary tree, and this is 4 different cases. Then the depth of the binary tree is log 4, is 2. Okay? Once again, this is very important. Distinguishing four different cases. Then we need log 4 is equal to depth. That is the number of bits to communicate between Alice and Bob. This is a table describing the whole cases for Alice's input and Bob's input when n is equal to 3. So suppose that Alice and Bob have 3-bit string. Then this is all cases Okay? Alice's input may be one of them, and Bob's input may be one of them. And in each entry, we can write the correct answer. The correct answer 0, 0, 0, 0. Okay, so this is the correct answer. For example, Alice 111 and Bob 000, then the total parity is odd. Okay? And for example, here, 101 and 001 again odd. 001 and 001 is even. Okay, so this is the correct answer. Now, Alice sends her parity in the first round. Alice sends her parity. That means Alice is telling Bob that her input is this side or that side. Right? Alice's input, Alice sends 1. Odd means Alice's input is here, upper side. Alice sends 0, that means Alice is, sorry. Alice sends 1, that means Alice's input is the lower side. Alice sends 0, now Alice's input is upper side. Then Bob sends, that is divided by this line. Okay? Bob sends 1. His parity is odd. That means Alice's input is this side. 0, that side. Now, by doing 2 red lines, by writing 2 red lines means 2 bits communication. 2 bits communication. Then you can see each part has a single answer. Right? By separating 2 red lines, each area has single answer. Namely, we are done. Okay. So let's do exactly the same thing for the example 5. For example 5. Now here, we do the same thing. For example 5. Suppose that now n is equal to 10. So Alice's input, Bob's input, like that. Alice, has one subset of 1 through n, 1 through 10, and Bob has also one subset of 1 through n. Okay? It's the same thing as before. Now, once again, Alice sends 1 bit to Bob. Maybe Bob send 1 bit to Alice, and maybe this may be Alice again. Maybe Alice again, no problem. That is not a big difference. Maybe Alice again. But by doing this, we have different cases, as before. Different cases. The question is how many? If we have m different cases to be distinguished, then we need log n bits. Log n bits for communication. That is exactly as before. By sending 1 bit, Alice sends 1 bit, then this table will be divided into 2 parts, right? Exactly as before. Now then, Bob sends 1 bit. Then again, the whole table will be divided into 2 parts. Then Alice sends, maybe here, and Bob sends, like this. Now we have how many? I don't know. It's how we have. Oh, I'm sorry. Yeah, it's a little bit complicated because this is the first divide, and then the second divide is here, but here. So now we have four different parts. Now the third is here, but this looks like divided in 2 parts, only this area. But just if you think a bit carefully, then again by sending 1 bit, we can divide the whole thing into 2 parts. That means we have at the same time something like this, but it's a little bit complicated. So anyway, by sending bits, this table will be divided into 2, 4, 8, 16, like this, like that. Okay? Now, this is a question. How many red lines do you need to realize this? To realize this means each rectangle, each small area has a single answer. Okay. So I'll show you this. I'll show you that. So this is a simple observation. We just look at the cells. We have cells like this. This means, it's this cell. There's one cell in each each column and each row. And this cell means no, Alice has everything and Bob has nothing. That means this cell is this set and its complement. Its complement. This cell is Alice set and its complement. And this is Alice set is 1, 2, and its complement is 3 to 10. Okay? And this is Alice is 1 and its complement. And Alice nothing, its complement. So we have a 2 to the n cells. 2 to the n cells. Okay, now. Okay, now suppose that we can divide the whole table into small rectangles by red lines. Now you can see that no two cells, some kind of cells can be in the same rectangle. No two cells. So for example, suppose that suppose that these two cells are in the same rectangle. This cannot happen. Why? Because the answer is what? 0. The answer is 0. Because this is Alice set and this is a complement. Alice set complement. So the answer is 0. What is the answer here? Each 1. This is 1. Okay? If those two cells are in the same rectangle, then this cell must be in the same rectangle. And this cell must be the same rectangle. But the answer of this cell is 1. Should be 1. Okay? Is that okay? Because it's obvious. This is Alice's set, and this is a complement. The same Alice's set, but this is more. Should be 1. Okay? I'm sorry, this is not 1. But this one should be 1. So, this is against the definition of rectangle. Same answer as rectangle. Okay. Now, okay. Now we are done. No two cells can be in the same rectangle of size 2 or more. That means each rectangle includes only one this special cell. That means we need at least 2 to the n rectangles, and by this argument, okay, we need log 2 to the n is equal to n communication bits, or depth n. So communication complexity is n. That is exactly the same as the obvious algorithm. Just sending everything. Good. So, this example 5, that problem is a hard problem. So there is no better algorithm than sending everything. Okay, just obvious algorithm. Okay, so we are done today. So today I showed you several examples which needs relatively small number of bits for communication, something like log n square, but there is another type of hard problem, meaning we need n bits. N bits means it's a no better algorithm than trivial one. Okay, so communication complexity is quite important. You have lots of applications, because just think of your pay for your cell phones. You're paying your money for the number of communication bits. Exactly, right? So this communication complexity is a very, very big issue, both in theory and practice. Great. So we are done today. The next week, I'm not very sure. What's the topic? I don't remember. But anyway, it is I'm not very sure what kind of topics I'm talking about. But anyway, see you next week.